Hello and welcome everybody to our first official proof videos for the geometry class. So yay! Well, technically we did proofs for logic, but now we're gonna do official proof that deals with actual geometry stuff. So here we go. Let's go ahead and get started with all of this stuff right here. First, we need to kind of clear some stuff, the final pieces of all the theorem postulates and also the properties that we have or the theorems that we have before we actually get started. Okay, so there are a few things I need to mention and then we'll go ahead and deal with the proof then. So here, the first thing we're going to talk about is we're kind of like going back a little bit, actually, back to chapter 2, where we first learned about the reflexive property, symmetric property, and also the transitive property. And most of you guys remember what it says in terms of what it represents then. Reflexive is just x is equal to x, and then symmetric is if x is equal to y, then y is equal to x, kind of like commutative. And then finally, for transitive, it is going to say that if x is equal to y, and y is equal to z, then that means that x is equal to z. And transitive property, you can actually have more than just 3 variables. You can technically have, like, say, 4 or 5 variables where you have a whole bunch of middlemen and all you're doing is cutting from the very beginning all the way to the very end. So the reason why I brought that up is all of these reflexive, symmetric, and transitive can be carried over also into angles when we talk about like degrees of measurements. So what I'm trying to say here is that for reflexive property, when it comes to angles, we can say the following. The measurement of angle x is equal to the measurement of angle x. Okay, or if you want, you can actually just go ahead and say the angle x right here is congruent to angle x. So either one of those would fall into the reflexive property category. Now, if you're wondering, is there a difference between the two, the way that I wrote it? The answer is yes. This right here is referring to the numerical value of the angle, but whereas here, this is basically just saying it by the name. Okay, so congruence, you're basically referring it to by the name and you're not looking at any numerical measurement of the angle. But whereas if you're going to say the actual measurement is equal to, like, say 15 degrees or 20 degrees, then that's where you put the m in front then. Okay, so we'll see that in action when we do the proofs. For symmetric property is the same idea. So if the measurement of angle x is equal to the measurement of angle y, then the result is that the measurement of angle y is equal to the measurement of angle x then, okay? Or the other way around is that if if x, the angle, is congruent to y, the angle, then that means that y, the angle, is congruent to x, the angle, okay? So exactly the same thing as symmetric, but except we're just talking about angles. And finally, for transitive property, so it is written as if the measurement of angle A is equal to the measurement of angle B, and if the measurement of angle B is equal to the measurement of angle C, then the result is that the measurement of angle A is equal to the measurement of angle C. Or when I look at congruence, we can say that if A is congruent to B, and if B is congruent to C, then the result is that the measurement of angle A is congruent to the measurement of angle C. Okay. So there's something kind of unique, which is going to be for like an upper math, but not necessarily for this one. The author liked to bring it up for some reason, and I might as well just go ahead and introduce it. If you can somehow prove something satisfy all 3 of these properties, reflexive, symmetric, and transitive, then we can say that that has something called equivalence relations. So once again, if you have something that you can prove via all reflexive, symmetric, and transitive property, then we can say that it has equivalence relations. So for example, let's say real numbers in this case satisfies reflexive, symmetric, and transitive, because any real numbers I put in here, it actually obviously works out. So it has equivalence relations then, okay? The other thing that I need to mention is that from the last video, there is a mention of the word perpendicular, but I didn't really define it. And again, that's something that's my fault, so I do apologize for that one. So here is basically the formal definition of perpendicular. So underneath it right here, you can see these are all the things that you can extract from it if you know that 2 things are perpendicular to each other. And by the way, this symbol right here, this upside down T, that is going to be our symbol for perpendicular. So if you ever see that then. So two sets are considered perpendicular to each other if, and it goes back and forth between the two because it's interchangeable, and this is the definition. First of all, each of them is a line, ray, or a segment. So that means the two sets that you're talking about has to be one of these three things. You can have a line and a line and a ray and a segment, or segment and a line, or maybe segment, ray, and line, and so forth. The second condition is that they have to intersect each other. So those two things that you just picked from the set from the previous one, they have to intersect each other. The third thing is that the lines containing them are perpendicular to each other. So that is going to be, kind of like a little bit of redundancy part right there. But here, the most important part, which is number 4, is that they form sides of a right angle. So for example, if I just kind of draw this on the side, let's say that we have a line, and then let's say that we have a ray. So you can see that right there, they are supposedly going to be perpendicular according to the way that I drew it. So according to our definition of perpendicular, then what that means is I am going to form this thing right here, which is going to be in a right angle. And according to our definition of right angle, that means that is basically saying that it's 90 degrees. So here I kind of drew a little diagram just to kind of illustrate what I'm talking about. So if you have two two sets in this case, that are perpendicular, then by definition, what you can say is that you are going to form a right angle. And technically, if you look a little bit closer, you probably form more than one right angle. If you have two lines that are intersecting each other, then they're going to form 4 right angles. But nonetheless, you have a right angle to work with. And then from there, by definition, you can say that the right angle is then equal to 90 degrees, and you can start working with the measurements. Unfortunately, you cannot jump from the very beginning all the way to the very end by thinking just transitivity. Okay, even though that, that's probably a lot more convenient, we actually have to say by definition of perpendicular and then by definition of right angle in order to go from perpendicular to 90 degrees and the other way around too. Okay. So now let's go ahead and talk about this last one right here. And then afterwards, we can go ahead and do our proof then, okay? Let's see. So here in the last part is, this is actually in relation to what we did last time about linear pairs. So this is kind of the same idea on the same in the same perspective of the perpendicular, right angle, and the 90 degrees. If we say that something is a linear pair, then by postulate number 14, then that means that we have two angles that are supplement to each other. And if two angles are supplement to each other by the definition of supplementary, then we can say that they're 180 degrees. And then so that's basically kind of like the procedure. And when you write out a proof, that's the steps that you're going to actually have to take. Now, you'll notice that I did not use something that is going towards the left. It's not an if and only if statement. So because if you remember from the last time we talked about this, supplementary doesn't necessarily mean that they are linear pair, because you can have an angle that is like this, and then you can have another angle that is going to be like this. And here you might have, like, say, let's say 80 degrees over here, and you can have 100 degrees right here, but they do not form a linear pair because they're not going to be right next to each other in that sense. All right, so here we go. Let's go ahead and write our proofs then, okay? So let's go ahead and get an idea as to how this works. So first we'll do a simple proof, and then afterwards we're going to go ahead and do a proof of a theorem that is actually in the book. So here's a first kind of like a little baby step as an introduction. So here in this picture, we are given that AC, okay? We are given that AC right here. Let me go ahead and draw it out. So AC right here, that is supposed to be equal to the length of BD. So that means that these two lengths are going to be equal to each other. So usually when something is congruent to each other or equal to each other, we can go ahead and maybe do a little symbol to indicate that. So here you can see that as a double dash right there. And what I want to do is in this picture, I want to prove that AB, the length, is equal to CD, the length. So similarly over here, AB right here, what I'm going to do is I'm going to go ahead and put a question mark to indicate that I'm trying to prove that is the same thing as CD over here, which I will also put a question mark. Well, you can probably see what's the procedure in this, because looking at the picture, they have BC in common. And if I use some sort of segment addition postulate, maybe I can go ahead and set them equal to each other and subtract that one piece of BC they have in common and get the result that I actually want. So let's go ahead and write the proof for this just to see how it actually works out then. Okay, so here we go. My first step. So first, I think I'm going to go ahead and start with the given. AC is equal to BD. And like we said, 99% of the time is going to be given, and that's exactly what's happening in this case. Now, earlier we were saying that, hey, if I want to go ahead and introduce A, B, and CD, I better go ahead and break each of these segments into their respective parts. So that is to say, let's go ahead and take AC and change it into AB plus BC, okay? For that reason right there, that is, if you remember, that's the segment addition postulate. Okay, the segment addition postulate, or SAP for short, which basically says that, hey, so long as those points are collinear to each other, then the result is that you can add the sum of the two smaller segments, and that'll be equal to the bigger one. And in fact, I'm going to go ahead and sneak in the other part as well over here to also say that BD is going to be equal to BC and then plus CD, right? And because it's the same reason, I don't need to introduce another step. If you wanted to, you can go ahead and do that then. But I'm just going to go ahead and save a little bit of step then because it's the same thing. All right, now let's go ahead and put these together. Now that I know what AC is in pieces and I know what BD is in pieces, why don't we go ahead and put them all together? Taking what we have right there, right? Let me go ahead and underline it. I'm going to go ahead and take this guy and throw it into this equation right here. And then I'm going to take this guy and then I'm going to throw it into this equation right here. So the result is that I am going to have, according to the equation number 1, with everything replaced, we have AB plus BC is equal to BC plus CD. And what I did right there is the transitive property, because I basically made a double substitution. I took AB plus BC and replaced it, and then I took BD plus CD and replaced it in there, okay? So that is supposed to be the transitive property, okay? And if you're wondering, okay, well, how do you tell the difference between transitive property and substitution? Well, I'm going to give you an example of a substitution in just a little bit, so then that way you can kind of tell the difference between the two. But nonetheless, hey, it looks like we're almost done, because if you notice now, what we're trying to get to what we're trying to prove over here, I just need to subtract what they have in common, which is BC. So it looks like my final step is to say that AB is equal to CD, and what I did right there was the subtraction property of equality, because I subtracted BC from both sides. Okay, and there it is. That's going to be our proof. So, nothing too fancy, nothing too long, just to give you an idea as to like how it actually works. All right, so now let's go ahead and do a proof with the geometry stuff that we've been dealing with. How about some angles related stuff? So here it is, theorem 4-2. Okay, so here's what the theorem says. If the angles of a linear pair are congruent to each other, then they are right angles. Okay, so if the angles in a linear pair are congruent to each other, then they are right angles. So here you can see that I drew a picture of two angles that are going to be forming a linear pair. So we have angle BAD and we have angle DAC in this case. Okay, so we are told that they are going to be linear pairs, so that means that's part of the given. Okay, so let me go ahead and write that out then. So as part of the given, I'm going to say that the angle BAD and the angle DAC, right, are linear pairs. So linear pairs, because that was part of our if statement. Then next we know that those two angles are also congruent to each other. So then that means that the angle BAD is going to be congruent to angle DAC. So meaning that these two right here are going to be congruent to each other. So I'm going to go ahead and draw those dash right there to indicate that they are equal or congruent. What I want to do is I want to prove that those are right angles. So in the picture, I need to show that right angles right here and right angles right here. And if you remember correctly, right angle basically means that they are of 90-degree measurement. So let me go ahead and write that over here. I want to prove that angle BAD and angle DAC are right angles. Okay. So let's go ahead and maybe tactically think about how to actually work this out. And then afterward, we're going to go ahead and write the proof. So first, the first thing that comes to mind is that, okay, well, we have something that's linear pair. And if you remember, linear pair by postulate 14 means that they are supplement to each other. So I can say that angle BDA is going to be supplement to angle DAC. And the reason why that help is, well, if they're supplement to each other, then that means that they are equal to 180 degrees if you add the two together. Just going to pull up to what I'm talking about, that's basically all this guy right here, right? So here, I guess if I can say that this is just simply x right here, and this is going to be simply y right here, then that means that x plus y is equal to 180 degrees. And looking at that part of, so that's pretty much all I can extract from them being a linear pair to each other. Now, knowing that BAD is congruent to DAC, then that means that x has to be equal to y. And that's nice because if I take that and plug it into here, then we would probably get something like, say, x plus x is equal to 180, 2x is equal to 180, so x is equal to 90. And bingo, there you go. That's going to be our proof right there to show that it's a right angle. So that's going to be our guideline. So let's go ahead and see if we can write a proof with all of this then. So here we go. Let's go ahead and start then. So number one, I'm going to go ahead and start with the given, right? So here we're going to go ahead and say that angle BAD and angle DAC are linear pair. So that one right there is going to be given. Now, technically, I could write the other given, but we're not going to use it yet. So I'm going to go ahead and save that for a little bit later when I'm actually going to use it. Next, after we said that they are going to form a linear pair, if you remember what I said, we need to talk about how they are supplement to each other. At this point, what I want to do is I want to start talking about algebra, looking at numerical values, so then that way I can manipulate some equations. So the next thing is the angle BAD and the angle DAC are supplement to each other, okay? And that one right there is going to be, as I said, postulate number 14, okay? Remember postulate number 14, as I said over here, which is going to say if two angles are linear pairs, then they are supplementary. You can technically write that whole thing down in the given if you want, or if you want, you can go ahead and say postulate number 14. I'll let either one slide, okay, just in case. But now that we have that, we can go further and say something about their measurement. So the measurement of angle BAD plus the measurement of angle DAC is going to be equal to, because we're talking about measurement already, 180 degrees. And right there, that is going to be the definition of supplementary. Okay, so definition of supplementary. All right. So I think that's as far as I can go with extracting information from this guy over here. So that means that we're going to go ahead and stop from there. Now let's go ahead and pull the second part and see what we can do with it. Again, if you look at our chart right here, my little guideline right here, it looks like I need to show, I already have this part right here. So next part is I need to basically say that those two angles are congruent to each other. And that's where, again, that's that second part coming in. So let's go ahead and write that out. So step 4, and I'm going to go ahead and use a different color just to show that I'm using the other part. So the measurement of BAD is congruent to the measurement of DAC. That part right there is given, right? That was the other given part. Now, as annoying as this is, you actually have to do it. We have to actually say that the measurement of BAD is equal to the measurement of DAC, because in part 4 we're given that those two angles are congruent to each other. That doesn't necessarily mean that their measurements are equal to each other. We need to talk about their measurements. So that fourth step to fifth step, that's actually necessary if we're going to play with equations. So that right there is just plain old definition of congruence. Okay, so congruence. Okay. Now we can go ahead and take step 3 and step 5 right here and make some magic out of it, because if I combine them together, that will now allow me to get something nice out of it. So here in step 6, what I'm going to do is I'm going to go ahead and do that combination as we said. Let's go ahead and take the measurement of BAD and replace it with the measurement of DAC. So putting it into this equation right here. So now we can go ahead and say the measurement of DAC plus the measurement of DAC is equal to 180 degrees. And that right there, that's actually my substitution. Okay, you notice how it actually works to substitution. I literally took one piece right here, right, of the equation and replaced it with this guy right here, and that's why it's called substitution. And there's a plus sign and everything else afterwards. Transitivity is just a whole bunch of equal signs where you're going to, again, cut from the middleman, cut out all the middleman and go from the very beginning to the very end. So that's the difference between the two. If you're just replacing a variable in an equation with something else like this, then yeah, that's going to be our substitution then. Okay. All right, we're almost done. Step 7. Hey, notice DAC and DAC. So I can probably put them together, right? So now I can say 2 multiplied by the measurement of DAC is equal to 180 degrees. And that right there, I can go ahead and call it a simplification. Okay, because what you're doing is saying 1 apple plus 1 apple is equal to 2 apples. All right, home stretch right here. Now we can go ahead and go to step 8, which is going to say the measurement of DAC is equal to 90 degrees. And the reason for that is division property of equality. We're dividing both sides by 2. And as the final step, we need to say that BAD is a right angle. So we have that all set because remember, we show that it's 90 degrees. So now we can say that angle DAC is equal to a right angle then. And there it is, going to be our last one, which is a definition of right angle. Okay. Now, technically, we were supposed to show that DAC and also BAD are right angle, but I can probably tell you that, well, that's basically just go ahead and taking step 6 to step 9. And instead of going to make a substitution for DAC, we're going to make a substitution for BAD. So it all comes out to be the same. And if those steps are the same, we're done with the proof because we did it already. All right, so there you go. That's going to be a pretty lengthy proof. So hopefully you guys are okay with it. Please leave a comment if you have any questions. And yeah, let's see what happens. And I'll see you next time. Okay, take care.